What is going on? We're back again. Got it's like what is this video? America's deadliest nuclear accident, killed in 4 milliseconds. Um, I haven't seen this yet, but I just watched one of these videos from this channel called Storified. At Storified. Uh, but it looks like he does like disaster videos, stuff like that. Apparently, no AI, so that's cool. But the video that I saw was about like some diving incidents, and guy seemed to be on top of his like accuracy details. I like that. So we're gonna go ahead and watch and react to this video here. America's deadliest nuclear accident. I don't think America has had too many deadly nuclear accidents. I know 3 Mile Island didn't have any deaths or even any casualties at all. So I don't know. I'm not sure on that. But yeah, I'm just gonna go ahead and react to this and see what it's like. Already looks like we have trouble here.
January 3rd, 1961. Emergency responders are dispatched to the SL-1 reactor after heat sensors triggered an alarm at 9:01 p.m. They already responded to 2 false alarms earlier that day, expecting this one to be the same. However, they have no idea that they are about to walk into the most gruesome nuclear accident in United States
That didn't look
history.
good. Yeah, no. Okay, no AI
After the
generated
Christmas
content. Yeah.
holidays, Army specialists Richard Leroy McKinley, John A. Burns, and Navy CB construction electrician Richard C. Legg began restarting the SL-1 nuclear reactor at the
Okay, so this
National
is SL-1. Okay, I've what the heck? Um, I've heard of this. I don't think I've ever actually looked into the accident that happened here. Um, not like a crazy accident, but of course, still not great. Nothing like Chernobyl or anything like that. But so interesting.
reactor testing station near Idaho Falls, which had been taken offline for the holidays. The most important part of this procedure required manually lifting the central control rod just 4 inches to reconnect
What?
it to its drive mechanism before SL-1 could start.
What? Did he say manually lifting the control rod? Oh no, this is not going to be good. I can already tell. This is not going to be good. Why? Like, okay, so I know like some of the older, like the first reactor designs, when they were first playing around with nuclear reactors, they actually used to like stack blocks of like graphite or lead around radioactive sources. I think graphite too, because it's like oh, okay. I'm not going to get too far into it, but just literally just picking up blocks and putting them around like radioactive sources and trying to get them to go prompt critical. So like that's pretty bad. But this was like super early on. Like I don't know when this. I don't know if he said when this happened, but like manually lifting control rods, like, but I assume he means with their hands. Oh no.
Producing power again. As Burns reached down to lift the 84-pound rod with his bare hands, Legg
84 pounds. Why is one for okay, even if this is your game plan, why is one person lifting 84 pounds? Oh boy, this is not gonna be good. This is not gonna
who
be
was the
good.
shift supervisor, stood beside him on top of the 9-foot reactor, while trainee McKinley observed close by.
9 feet. That's a
However,
pretty small
the
reactor.
3 young technicians had no idea a reactor designed to produce 3 megawatts
Okay,
of
3
thermal
megawatts.
power is about to surge to nearly 20 gigawatts in just
20.
4 milliseconds.
Oh wait. Oh, holy shit. So 20 gigawatts would be 20,000 megawatts. Holy fuck. So that's like 7 times. And that, so you said thermal power, that's, or thermal, yeah, thermal power. So 3 megawatts of thermal power comes out to about a megawatt of electrical power once you do the heat exchanging and all that. And to boil water and whatever. But oh, that's crazy. So if you don't know how reactors work, they generally you're not you're not sucking energy directly out of like the nuclear fission. You're like just using it to generate heat, which then turns water into steam, which then turns a steam turbine, which so literally the whole world still runs on steam basically. Unless you have wind or solar power, it's pretty much steam energy. Whether you're burning coal, natural gas, wood chips, wood pellets, or you're playing around with nuclear stuff, you're generating heat to turn that to boil water and spin a turbine. I mean, it's all the world still runs on steam power. It's kind of crazy. We just haven't found a better way to do it, except for I guess wind and solar, which aren't reliable for baseline energy generation, but or not baseline, base load energy generation. But yeah, that's oh boy. Okay. All right. So 3 megawatt heat thermal reactor. Okay.
Turning their simple task into something far more
I
horrifying.
don't want to go too
A
far into this
surge of
yet.
almost 7,000 times the reactor's design power should have been impossible. But the stationary low-power reactor...
Well, I mean, I guess it depends on what they did here. It wasn't an ordinary reactor. Oh no. Oh no. Yeah, I guess it depends on what exactly how they designed it. Maybe it would be possible. Oh shit. I'm not like a nuclear expert, just full disclosure, I'm not like a nuclear physicist or nuclear engineer or anything like that, but I know a little bit about it, but like, oh no.
or SL-1 wasn't an ordinary reactor. It was an experimental military design developed on a crash
God, it's
timeline
military
for
grade.
remote Cold War radar stations across North America's
On a
most
crash
isolated
timeline.
regions as part of early warning systems
Oh,
against
Cold
Soviet
War, of
bombers.
course.
However, supplying these sites with power proved near impossible as they were cut off from power grids, isolated from transport links, and
Which
subject to
that's okay.
extreme
That's
cold
a
during winter.
good idea
Rather
for
than
a
abandoning the program,
small reactor.
military contracted nuclear specialists at Argonne National Laboratory to design SL-1, an easy-to-transport, small-scale boiling water reactor, which allowed the stations to generate...
So yeah, when they say boiling water reactor, that means so there's two kind of main ways to sort of make the basic sort of not reactor designs, not it's not the full design of the reactor, but it's like the basic way that you build the reactor containment and stuff, not the containment, but like so with like a boiling water reactor, the water that is in the reactor is like the coolant is actually going straight to the heat exchangers, which is going to the water for the steam turbine, turning that water into steam and turning that. And then there's the pressurized water reactors. Those are, I don't know if you can say that's safer, but maybe a little more contained essentially because you have two loops. You have one that's actually like the coolant, and that actually goes through and heats up another loop of water that then goes to the turbines, which gives you sort of containment from the actual steam power part of the facility. And the boiling ones are not as contained basically, so you can have more issues with radiation leaks and all that contamination. But I mean, a lot of reactors, even big ones, are boiling water reactors. It doesn't make them inherently dangerous. It's just you can get more contamination in more places, so that's more things if you decommissioned, you have to more parts you have to worry about disposing of in a safe manner, but probably not super important here, but that's just, I don't know, just something to think about.
Heat and electricity entirely on their own. But its practical design created deadly vulnerabilities.
Design.
In order for the reactor to run for
Manually
years
controlling
without refueling, the
control
engineers loaded
rods.
SL-1 with 14 kilograms, about 30 pounds, of highly enriched 93%
Holy
uranium-235 to
shit.
keep the station operating for up to 3 years.
Oh my god. Okay, so 30 pounds of 93% enriched uranium. 93% enriched uranium is weapons grade uranium, which I guess during the Cold War the US had a lot of that laying around, but okay. So, first for some comparison here, a normal reactor, like just normal commercial grade municipal reactor, hooked up to the power grid, that kind of thing, is going to use like around 20% enriched uranium, which is still fairly highly enriched. There's sort of a different there's it's not a linear thing with enrichment to how weapons grade it is, but just just take that, just relatively figure that like 20% for a normal sort of commercial reactor. Chernobyl, the RBMK reactors that they had were anywhere from like 3 to 5% enrichment because of their design, which wasn't the best design, but it didn't need highly enriched uranium or even like, they call it, it's the 20%, it's called like high assay low enriched uranium, something like that, halu fuel or something like that. But the like Chernobyl was using like very low enriched uranium. I mean, so when you pull uranium out of the ground, you mine it out, it's about, I think it's like less than 1% U-235, uranium-235, and the rest is mainly U-238. And U-238 is pretty much inert. It doesn't, I mean, I don't know if it's even slightly radioactive, maybe, but it's like super, super, if it is, it's super, super long half-life. I think that might actually be the stabilized stuff. But so U-235 is the stuff that's you're looking for, and you're coming out of the ground, it's like less than 1% enriched. And once you enrich it, I mean, it doesn't take that much to get it to like 3 to 5% enrichment. And that's what Chernobyl was using. Yeah, Chernobyl, we all know about Chernobyl. So just, consider that. That doesn't, again, because Chernobyl was pretty low enrichment, the enrichment isn't necessarily the danger factor, but we're already talking about manually handling the control rods. And now we've got 30 pounds of 93 of weapons grade uranium, which so now we're not just talking about like prompt criticality. We could end up with like super criticality. Think of like a fission bomb. You shouldn't you shouldn't be able to get a reactor to super criticality. Prompt criticality, sure. I mean, yes, you could generally, usually they're going to run subcritical, so you're not getting a runaway, you know, nuclear reaction. But even Chernobyl didn't. I don't remember if they went prompt critical. I don't think they actually did. They may have, but even if they did, it was all contained within the reactor vessel, and then there was a hydrogen explosion that blew, everything apart within the reactor, blew the reactor vessel apart and spread all the contaminants. So, oh boy, 93% enriched uranium. Like I say, weapons grade uranium, 30 pounds of it shoved into one tiny reactor just to make it last, longer, rather than having like a store of the stuff on site that you could refuel the reactor with. Oh no. Oh no. All the pieces are coming together. Whew.
This was a
We're only
higher
3 minutes into this.
concentration of
We're only 3 minutes into this video, and I'm almost to 15 minutes, and I'm already just like, I can almost like tell you what's gonna happen. Like I'm guessing they're gonna pull the control rod too much, and the thing's gonna go prompt critical, and it's gonna boil off the coolant water, which should should stop the nuclear fission. But if it gets too hot, which of course if you've got this highly enriched uranium in there, it could just keep going and have, go prompt critical, and and cause it to essentially just a mechanical explosion, which is going to tear the whole vessel apart. Not even a chemical explosion, but just like a mechanical explosion. Holy crap, dude! You don't mess around with steam. Holy fuck.
Uranium than the contents of the Hiroshima bomb.
Yeah. So the Hiroshima bomb. I keep pausing it, but the Hiroshima bomb was about 80 to 85% enriched uranium. Okay, that's what you need for the type they were using with the Hiroshima bomb, little boy. With Fat Man, which just was an implosion type device. This is what the whole Oppenheimer movie was about: designing the Fat Man device, really a gadget to make sure it would actually explode. Because with an implosion type, you need like insane amounts of timers and all this crap to actually make sure everything actually implodes at exactly the right time to shove this stuff down into. That's using plutonium though. Little boy was using uranium, so plutonium is a different thing. But uranium, oh god. So they're using like modern day weapons grade uranium in this stuff. Like, well, say modern day, it's a little different now, but like back then in the Cold War, this was after World War II. They were probably making much more enriched uranium for the fission bombs that they were making and testing. They weren't really using them, but they weren't using them in wartime, but they were testing them all over the Pacific and shit. Oh boy, this is so not good already.
SL-1's core so sensitive that even small movements of its control rods caused sudden, dangerous spikes in power.
Yeah.
To address this issue, engineers introduced thin boron aluminum burnable poison strips inside the reactor core.
So okay, so when they say poison, they basically mean that it will stop the reaction. That's what like a nuclear poison is. It essentially stops the reaction from happening. The neutrons will get absorbed by something else that will stop them from hitting their actual target nuclei, and then you don't, the reaction just stops. But still,
these strips absorbed excess neutrons, which slowed the rate of nuclear fission and theoretically would prevent the sudden power spikes while helping the reactor operate safely.
Theoretically.
However, this was a new and untested idea, and over time, extreme heat and corrosion could cause pieces of the boron to break off and slip into the narrow gaps around the fuel, jamming the channels the control rods had to move through. And unfortunately for the three men, this is exactly what started to happen. Between February 1959 and December 1960, SL-1's control rods jammed over 80 times. To make things even worse, unlike commercial reactors sealed inside thick concrete containment structures, SL-1 operated inside a thin, steel-walled building called ARA 602.
Is that a grain bin?
Its unsealed outer shell was intended mainly to keep out the weather and serve as part of the cooling system, not to contain an accident. On top of that, instead of having permanent shielding made of thick, dense materials to absorb deadly gamma rays and high-energy neutrons around the radioactive core, the men had only a few movable lead blocks for protection and often stood just a few feet away from the small 4x4 reactor. With so little shielding, their radiation exposure near the vessel exceeded a modern worker's entire annual safety limit in just minutes. Despite
so modern day reactors will have a containment building that's mainly not, it's not there for a nuclear explosion. It's there for a hydrogen explosion, and generally there'll also be a thing to actually burn off hydrogen, and so you don't have to worry about it building up. But or even even like a steam explosion. But like, oh man. So they didn't really have a containment, but they were working, I'm guessing, looks like an isolated area, so they didn't really have to worry about like people around them, but still you don't want to send contaminants flying through the area. Either way, man. And then movable lead blocks so they said it exceeded a modern day radiation worker's yearly limit in a few minutes. So that means, so the way that works is a modern radiation worker you you only get I think it's like 100 millisieverts per year. So 100 millisieverts. Now, you're exposed to background radiation all the time from the Earth, from like radon gas that seeps out of the Earth, from cosmic rays and stuff like that hitting you, various sources that just occur naturally, and your body's made to build to protect you from that. Like you easily repair from that kind of thing. But so background radiation is usually like 10 microsieverts to like 20 microsieverts, depending on where you are. And so that's like a millionth of a sievert. A millisievert is 1,000 times more than that. So we're talking about you can monitoring radiation worker can get up to 100,000 times their normal background radiation per year. Essentially, they could be exposed to it, and that's considered safe, which is pretty crazy. So like, and I say 10 to 15 microsieverts. That's microsieverts per hour. So this would be, I'm talking, that's more like, this is dose rate versus dose. So it's 100 millisieverts per year they're allowed to get. So you'd have to figure out that of like how many hours there are in a year and figure out the math there. I'm not going to do it. That's beyond the scope of this video. But if you were exposed to 100 millisieverts all at once, you still wouldn't necessarily get like radiation sickness or even have perhaps a higher level of cancer rate chance in the future. It's just that's where they set the limit. Most radiation workers are never going to hit that limit in a year. They just won't. Radiation work is generally like it is so well protected, so shielded, especially like in the US. There are very strict regulations on that. So like you're never really ever going to have to worry about that, but that's just like the limit that they've set for like modern day radiation workers. And generally, even if you hit that limit, you're not really going to have to worry. But that's considered like the generally safe kind of limit to where you don't have to worry. The worry starts maybe many times that, could be even up to 100 times that. Just it depends. Everything kind of depends here. Like it depends on how concentrated this dose is, like if it's like a beam or if it's like a spread out kind of thing. All that matters, right? Um, but yeah, so they're receiving their yearly dose of in a year. I mean, in a few minutes. Oh boy, that this is a really bad design. And I guess this is what this said 1960, so this isn't that long after. I mean, once we figured out, I mean, we had reactors that we were testing back during World War II before we actually made the bombs, and and then after we made the bombs, we were still testing. But this is like this seems like this is just rushed. This is just this is military grade. Oh boy.
Building a facility that pushed the limits of safety, officials went ahead with their plan to use ordinary recruits to operate SL-1. So Argonne incorporated a simplified control system that could be taught on an intensive 9-month Army qualification program.
Oh boy.
As a result, SL-1 relied on just 5 cruciform control rods to manage its power output.
Holy shit.
This was highly unusual. For comparison, Chernobyl reactor number 4 used 211. And
Well,
the arrangement...
I mean, to be fair, Chernobyl reactor number 4, and I think they only had 4 of them, but all of the reactors, they were giant RBMK reactors that, like, they had like all those things there. You can see I think the gray ones are actually the control rods. All of the colored ones are the either the fuel rods or different things that they could irradiate and different like research stuff. But yeah, this is that's also the Chernobyl reactors were hitting like their nominal like thermal output was 3,300 megawatts, which are 3.3 gigawatts thermal. So about 1 gigawatt of actual electrical energy. But like, oh man, that's That's a huge. I mean, it's a huge difference. But these are small reactors too. So that's like a. I understand that they're not going to have 204 control rods because they're much smaller reactors. So you can see the size of that thing. This diagram right here, where you are walking across this thing is like it's also like the top of the reactor. It's like a giant lid, and I mean each one of these like blocks here weighs like like 1,000 pounds or something. It's insane. It's a lot of mass. So here, yeah, it's this is a huge floor you can walk across. You can still visit the Chernobyl stuff too, not this internal part here, but not a reactor number 4, but I think they'll take you to like reactor 1 or 2 or whatever, and then you can tour around the reactor room floor and actually see the top of the reactor vessel and all of these control rods and stuff. And it's pretty neat. But they had like cranes, overhead cranes they were using to lift these rods up and actually like change out the fuel and all that stuff. So like this is a big facility. I mean, this is a massive facility compared to these little 3 megawatt reactors they were building here, the SL-1. So, but I mean, okay, so just trying to compare it to Chernobyl. I mean, that's I guess what everybody knows about is Chernobyl, but like that's not a great comparison though. This, I mean, you compare it to like any, I don't know, any like research reactor at like at a university. They don't tend to have a ton of control rods or ton of even a ton of fuel rods, but they don't usually have blocks of just fuel shoved in there. That's oh boy, this reactor. Oh boy, I can't.
The limited number of control rods meant that the central rod was extremely powerful. It was positioned directly above the core's highest concentration of neutrons, and if it were withdrawn just a few inches too far, it could drive the reactor into a prompt critical state with deadly consequences.
This is a terrible design.
Control rod should be powerful enough to shut a
Yeah,
reactor down
it should
or
be
start it
balanced.
up all by itself.
This is
But
a
at
terrible
SL-1,
design.
everything that followed came down to that central control
Of
rod.
course.
You see, in order to generate
Single point of
electricity,
failure.
nuclear reactors use fuel rods, or in SL-1's case, fuel plates that contain nuclear material. These materials naturally emit particles as they decay, producing a tiny amount of heat.
This is
But when
terrible.
these fuel plates are brought close together, like in a nuclear reactor, the released particles react with the other nearby fuel, setting off a chain reaction called nuclear fission that generates massive amounts of heat.
God.
To control this reaction, control rods are used to absorb those particles. By moving these rods up or down inside the reactor, the rate of the chain reaction, and therefore the amount of heat produced, can be precisely controlled. Reactors then use this heat to turn water into steam, and steam into electricity.
Not the water in here though. You can see here the reactor vessel. You have so much water. You're pumping water through. Yeah, you can see through into the steam generator, right? So you're making this is the boiling water reactor looks like. The pressurized water reactor would have another loop, so you keep the water from the reactor, the coolant water, outside of that steam generator. Now, in the RBMK reactors, you had coolant, which was water, and then you had a moderator, which was graphite. Those graphite blocks that blew the hell out and irradiated everything. That was really probably the RBMK's biggest issue, or Chernobyl's biggest issue. That where they had these, just because normally in this type of reactor here, that coolant water. Let's go back. You see the water in this vessel here. That you could see it like right. You can see the line right above the little play button. That water is acting as a coolant, but it's also acting as the moderator, because water, this is, I don't know if it's heavy water or whatever, but it acts as a moderator to slow down the neutrons. So as the neutrons are coming out, they're coming out screaming fast, because this uranium is always going to be putting out neutrons. It's radioactive, so it's putting out fission products and neutrons, but the fission products aren't going that far. They're pretty slow. The neutrons are going to be coming out very fast. They call them fast neutrons for obvious reasons. There's a lot of very obvious terminology in the nuclear stuff. Not always, but a lot of it's just very it's almost like childlike terminology. Like the chances of like hitting a neutron hitting like another nucleus is they call it, they measure it in something called barns, which because it's like hitting the broadside of a barn. You've ever heard that term? They literally measure it in a unit called barns. It's it's so ridiculous. But what they do, they use the water to slow down the neutrons. So they slow down the neutrons will slow down in the water, and they become what they call thermoneutrons. So they're moving at a pretty slow rate, and that gives them a much higher chance to hit a target nuclei, right? A target nucleus. And if you remove that water, the reaction should slow down. However, with this highly enriched uranium in here, this weapons grade uranium, that can be not as feasible. But in the RBMK, you had, I think it was just light water, and you had graphite, and the water. So instead of heavy water, which is deuterium, which is mildly radioactive, and then there's another thing called tritium, which is like heavier water that's much more radioactive. But uh, in the RBMK, you're using just light water, and with that light water, it doesn't really act as good as a moderator, but you don't have to have all that deuterium. And there's a huge reactor, so you didn't have to have all that because it takes more time and energy and money to produce that, and the USSR wasn't worried about all that. So, and they weren't as worried about safety. Well, look at this thing. But so in the RBMK, you had the water was acting as just the coolant, and you had the graphite blocks in there that were acting as the moderator to slow down the neutrons to get them to actually give them higher barns, essentially give them more of a chance to actually hit other nuclei and cause more fission. So in this reactor, if the water goes away, this one here, which is more like a modern reactor, the boiling water reactors, if the water goes away, if it boils into steam, it won't act as a moderator anymore, and the reaction should slow down. Now, even with the control rods, well, the control rods are still pretty important, but because they're actually made of stuff that will just absorb the neutrons and the reaction will not work. But without the water in there, the coolant's gone and the moderator is gone. So now you've got, even if it starts to overheat, it still shouldn't. Oh, sorry, I squeaked. It's still damn teeth. It still shouldn't be able to actually keep fissioning. So it should just stop. But remember, this uranium is really highly enriched. So if that happens, oh man, oh boy, this is a terrible design. Let's keep going. Oh shit.
Like in a nuclear reactor, the released particles react with the other nearby fuel rods up or down inside the reactor. The rate of the chain reaction, and therefore the amount of heat produced, can be precisely controlled. Reactors then use this heat to turn water into steam, and steam into electricity. Operators at SL-1 were aware of how this worked, but it's uncertain if they were aware of just how sensitive that central rod was, since they were just ordinary technicians. And this is when things became
With 9 months of intense
dangerous.
training.
Before the holidays, SL-1 was made subcritical by fully inserting its control rods into the core. While it was technically offline, this didn't stop nuclear reactions
Right, you
entirely.
never want to fully shut down a nuclear reactor.
Still took place inside the reactor, meaning it was as vulnerable to control rod movement as it was during normal operation. As Burns began restarting the reactor, he tried to lift the central control rod number 9 from SL-1's core, but instead of the intended 4 inches, he, for whatever reason, yanked it 20 inches. Within 4 milliseconds, SL-1 went prompt critical. With nothing keeping fission in check, the raised control rod triggered an unstoppable chain reaction, devastating the
water
reactor.
boiled off.
Neutrons multiplied like wildfire. As SL-1's power output surged past 20,000 megawatts. The massive burst of energy flash-boiled coolant water around the core's fuel. transforming it into superheated radioactive steam. Pressure inside the vessel instantly spiked from 20.4 atmospheres to over 650 atmospheres. And as the steam expanded, a violent explosion slammed the remaining...
So this is essentially what happened at Chernobyl. You had this intense buildup of steam. The reactor went prompt critical. It ran away with thermal energy, and then the steam boiled off. The water boiled off into steam, but the steam boiling off wouldn't. Now you don't have a coolant, and it just keeps getting hotter and hotter and hotter. And the moderator is still in there. They lowered the control rods, but they couldn't get them down fast enough, and it built up way too quick, and that caused a steam explosion, which then a bunch of hydrogen was released, and then they had hydrogen explosions and all that. So yeah, but this is a little different because you're boiling off all the water. So once you're boiling off the water here, the water is your coolant, and if your coolant goes away in a reactor like this, that's also your moderator. So it should stop the reaction, but either the reactor vessel, which is a pressure vessel, was either too small, not strong enough, or there was just too much enriched uranium, and they could not. It was too many neutrons, even without the moderator, to even control it enough. Which this is, oh man, this is such a terrible design. Fuck.
Water into the top of the reactor with so much force that the 26,000-pound vessel jumped 9 feet into the air.
Holy
Burns,
shit.
who was right next to the reactor, was slammed against a concrete wall as SL-1 ripped apart, while metal shards catapulted in all directions, severely injuring McKinley.
Burns.
But the chaos wasn't over yet. The blast violently ejected the steel shield plugs from the top of the reactor, unleashing radioactive water and debris all over the 3 men.
So it didn't fully blow up like Chernobyl did, but
towards Richard's leg, impaling him through the groin and out his shoulder.
Certainly enough.
Meanwhile, heat sensors above the reactor triggered an alarm, immediately alerting the National Reactor Testing Station Fire Department 8 miles away. The firemen had already responded to false alarms from the facility that morning and afternoon, so they expected.
I mean, when it comes to radiation,
however, at 9:17,
so when it comes to radiation, your 3 main safety factors are shielding, distance, and time. So you want to have as much shielding as you can, as much distance as you can, and as little time as you can. They had 0 shield. Well, they had some lead blocks that they could move around, but at this point, the reactor has disintegrated, or just not fully disintegrated, but just blown apart. They've got water with contaminated water all over the place because that steam. Oh man! And then time-wise, these guys are 8 miles away. So they've got like pretty much no shielding now. They're right on top of the reactor, and these guys are 8 miles away, driving through what looks like snow, across ice. Who the hell knows? This is everything about this is just so terribly designed.
When a health physicist and the assistant fire chief entered the adjacent building wearing air tanks and masks and approached the reactor building stairs, their radiation detectors jumped to 25 roentgens per hour.
25 roentgens per hour. So, what did I say before? Background is usually like figure 10 microsieverts per hour. A Roentgen is roughly, I think it's 10 millisieverts per hour. So that's already like 1,000 times more than just normal background radiation, and which isn't necessarily dangerous yet. But then 5 times that, or was it 20? What did he say? 5 times? 25.
Radiation levels and masks. With Walmart's summer
style.
Oh
no, Walmart!
An impression.
Damn it! Sorry.
And masks and approached the reactor building stairs. Their radiation detectors.
Whoa. Okay, so 25 times 10 mil, so 250 millisieverts per hour. So in 1 hour, roughly, what is that? Like less than half an hour, you're going to get your yearly dose of radiation for a normal radiation worker. 100 millisieverts. That's the full dose, but this is a rate, not a dose. So it's the dose per hour. So 250 millisieverts per hour. Oh wow. So yeah, within I don't know, within a half hour you're gonna get. I'm not doing all the math on that, but within a half hour you're already gonna get your yearly dose.
Up to 25 roentgens per hour. Unable to believe the radiation levels could be that high, and suspecting their
Yeah,
detectors.
because nearly or most of the time in a radiation facility or yeah radiation facility, a nuclear facility, you're you're not going to detect any radiation like above background for the most part. If you do, something has usually gone very wrong. You know, it's only going to be like inside the pressure, the nuclear pressure vessel where you're actually going to get radiation. So, you know, there's so much shielding and safety generally, unless you're standing above the reactor with a couple of lead blocks, and really there isn't much shielding to begin with. Then yeah, that's oh my oh. Okay, so
Faulty, they were
they
forced
played
to
it safe
retreat.
and backed
After
out.
grabbing a higher range detector, they returned and carefully ascended the stairs. But this time, the meter maxed out at 500
Holy
roentgens per hour.
shit. This is the same issue they had at Chernobyl where they couldn't get a strong or they're all their detectors they thought they were either broken or they because they kept maxing out at like what was it? I think it was like 3 Roentgens or something, and they kept saying no, there's no way we're getting that measurement. We need a higher level detector, 500. So now we're talking about 250 millisieverts, so 25, so times 4 would be 1,000 times oh god times 5 is going to be 5,000 millisieverts per hour. So that wow. So you're getting a yearly dose in within minutes. I mean that's super dangerous. I mean again, the yearly dose is not necessarily going to give you like radiation sickness or cancer or anything like that, but if you're there for, if you were there for an hour, you would almost certainly get radiation sickness. This is, I mean, even within that, the 500, so 5,000 millisievert, that's your daily dose in what, an hour, 100 times 60 would only be, that would be about 6,000. So yeah, it's your yearly dose in about a minute. Oh shit. Yeah, yeah, so holy shit, 5-10 yearly doses. I mean, 5-10 minutes of being there, you're getting pretty fucked.
They managed a quick look
Oh
into the
my
reactor
god.
room and saw scattered debris, but no sign of the missing operators. With radiation levels reaching dangerous doses within minutes, they retreated once again. It took the emergency responders over an hour to plan and attempt a full
Holy
entry into the
shit.
reactor.
Over an hour. So again, they're playing it safe, which is they I guess they've already figured out that this has gone catastrophically wrong. But they're playing it safe, but like over an hour, the guys in there are they're going to be. I mean, even if like the blast didn't kill them and all that, they're probably looking at well over 500 Roentgens per hour, which is, I mean, this is so bad. This is so bad. Oh my god.
By 10:30 p.m., the lead health physicist and operations supervisor arrived on site. But halfway up the stairs, they heard faint moaning. Quickly
Oh,
making their way into the
no
reactor
way.
room, they found McKinley barely alive, and a second operator, Burns, with no detectable pulse.
Holy shit. So I'm guessing the guy that got impaled is dead, but where's he at? But okay, so one of them is actually still alive. What? Oh man, I'm guessing he's not going to be alive for much longer. I mean, even if he doesn't get radiation sickness, he may have massive internal bleeding from this explosion that just happened. I don't know what he got, debris got hit by, but still, holy shit.
Joined by 3 more health physicists, the team returned with a stretcher and successfully evacuated McKinley. He was loaded into a panel truck
Look at that
and
old
rushed
ambulance.
into an ambulance. But before the ambulance reached the nearby Highway 20, McKinley was pronounced dead.
Jesus.
The
Yeah.
contaminated ambulance, still carrying his body, was driven into the desert and abandoned for
Wow.
several hours. In the meantime, the third operator was still missing, but recovering him would be anything but simple. After evacuating McKinley, 4 firemen entered the building at 10:38 p.m. and made their way into the reactor room, but found no sign of leg among the destruction. It was only when one of them scanned the ceiling with a flashlight that responders realized what they thought was debris was actually leg, impaled and pinned to the ceiling.
Holy shit. Dude. Oh, he got hit with, okay, he got hit with one of the, so he didn't get hit with the control rod itself, which I would assume he would have been the control rod because he was, well, if he was lifting it in front of his face and that exploded up, okay, so then he just happened to be unfortunately standing right on top of like one of the other, one of the shield plugs that was just, yeah, okay. Holy shit. Yeah, that sucks.
Reactor by the number 7 shield plug. However, his radioactive body couldn't simply be pulled down. Doing so risked the shield plug that pinned him falling back into the open reactor core, dislodging fuel elements and triggering a second criticality event.
This is,
to make it even worse,
I don't know how many times I
leg
can say
was
this, but this
positioned
is
in the most
a
radioactive
terrible
part of the
design.
room, with meter readings capping at 1,000 rontgens per hour.
Oh my God.
Standing directly
So we doubled it already, and that's probably just the max that meter reads.
Safe course of action, a team of specialists began designing the equipment needed to reach leg and Burns without endangering rescuers. Burns' body could be removed by the next day on January 4th.
So he was already
and
dead,
taken
so they just
to the
left him
same
there.
facility as McKinley for decontamination, leaving the most dangerous recovery yet. It would take
at this point,
a
it's
week
literally
before
just
Leg's body
body
could be
recoveries.
reached,
It's
as
not even a
engineers
rescue
designed
mission.
a special stretcher system suspended from a crane outside. When everything was finally ready on January 9th, small teams entered in short rotations, each spending no more than 65 seconds inside the reactor room.
Did you hear that? 65 seconds. So they're this is so much radiation. They're getting, and again, they're once they go in for that 65 seconds, somebody probably did the math on that and figured, all right, you got about a little over a minute before you're done. This is you're done. So they're getting that 100 millisieverts within a minute there. Or, that's, and then again, this was double too. So they're getting like 200 millisieverts in like that time. That's, wow, that's crazy. That's crazy. So yeah, so they're just going to rotate teams, and once they get one part of it done, they leave. They're done. That's what I was talking about before. Shielding, distance, time. You really can't do anything with shielding. There's not really like a giant lead suit you can put on, and even that's not going to stop everything. But and then distance, you have to be right there. So you pretty much have to go back to time and limit how long each guy is in there. Wow, this is...
The plan meant they would receive non-lethal doses of radiation, around 27 rontgens, but still enough to raise their lifetime cancer risk. Using long, hooked poles, they pried Leg free from the shield plug without standing beneath him, guiding his body into the suspended stretcher. The crane operator lifted him clear of the room, and Leg was taken to the same facility as the others, where all 3 men were prepared for burial in lead-lined caskets, sealed inside metal vaults and covered with concrete. Wow. Investigators could never determine exactly why the control rod was lifted more than 4 times higher than intended.
I don't know, human error? I mean, any number of things could have caused that, but let's see what they say.
Most likely cause was that a mechanical jam likely forced the men to pull harder, while rumors later speculated about personal tension.
And if there's just one guy pulling this out, I don't know, maybe there was more than one guy pulling it out, but still, if it's stuck, what are you going to do? You're going to probably wiggle a little bit and maybe pull it harder. So, yeah, you might very well end up just yanking that thing right out of there. They were supposed to pull what? It said 4 inches, which is I mean, what do you do? You got like a ruler down there just measuring how far you're pulling it out, and then they ended up pulling it up 20 inches for whatever reason, and that was all it took. Within seconds, they were dead. Well, two of them were. Holy shit.
Including an alleged affair, none of which were proven.
Oh god.
Whatever
Okay.
the reason, the
There's
three
possible murder.
operators
They
were
all
all in their
it was a
20s,
murder
with
suicide. That's what
Burns
it
just
was.
22. The disaster ended the Army's top secret portable nuclear power
Wow.
program and transformed reactor design, leading to new safety systems, stricter training, and the
Yeah,
one
new
broad
safety
rule
systems.
that ensures
Any
such a
safety
tragedy
systems would have
can
been good
never
here.
happen again. Today, SL-1 remains the only fatal reactor
Only
accident in
fatal
American history.
reactor accident. Wow. That's crazy.
That little piggy booked a villa.
Okay. Whoa. All right, Miss Piggy. Only fatal reactor accident in U.S. history. That's crazy. I don't think I've ever heard about this story here. I've heard of SL-1, but I heard it was just an early reactor and they had an incident, but I never actually looked into what happened. But I mean, it's not like your Chernobyls or whatever, those sorts of things. Your 3 Mile Islands and 3 Mile Island there weren't even any fatalities with that, or anything. They didn't even have a full meltdown or anything. So this, oh boy, this wasn't even like a meltdown. It was just, oh man, that's crazy. That's wow. Uh, who was that? Shit, I already lost it. Storified. At Storified one. I'll leave a link to his channel in the description and the original video. But yeah, that's some crazy shit right there. I I was uh I was not prepared for that. It's got to be. I mean, that's worse than the Chernobyl reactors, the RBMKs. That's a worse design than them. Aside from the water thing, but the whole like weapons grade uranium, because they wanted it to last as long as possible without refueling, and oh man, that's unfortunate. Those guys should have had better. The engineers that designed this, I mean, these are just technicians. These are the guys who were just working at this reactor, trying to do whatever, do testing so they could get it operational, get these like shipped out to whatever sites. But the engineers that design this stuff, man, they really did these guys dirty. This is bad. That's so bad. That's unfortunate, man. Just whew. Anyway, there's your daily dose of ridiculousness. Daily dose, daily dose of the internet. Uh, yeah, that was interesting. I haven't heard about that yet, but I hope you enjoyed it. Enjoyed my commentary on it, and I know I can ramble on about certain topics for a long time, but yeah, yeah. Drop me a comment. Drop me whatever the other things are. Just go hit up Storified. Great channel. Very seems to have very detailed videos, and he seems to be pretty accurate. Seems like he does his research, and no AI. So if you're not a lover of AI, then there you go. But yeah, have a good one. Peace.